Now, I will start the second lecture of week 9 of this course. In this lecture, I will continue the discussion on geometric structure factor, okay, and I will show in detail how to calculate the geometric structure factor for any crystal. Okay. So, week 9 lecture 2 will be geometric factor. I will also talk about the missing peaks in crystal structure in an XRD pattern. Okay. So geometric factor basically gives the role of the basis, okay. And here if you take an orthogonal cell, for example, if you take an orthogonal cell, okay, that is alpha equal to beta equal to gamma equal to 90 degrees. So, if you take such a cell, then the different the different atoms in the cell in unit cell they scatter with different phases, scatter X-rays with different phases. Okay. So, this is similar to when we talked about the Bragg scattering. We said that there is a phase difference between the different X-rays falling on different lattice planes. Okay. Here we are talking about the phase difference between the X-rays scattered by different atoms of a unit cell, and this phase difference delta. So, the phase difference delta is given by this expression 2 pi h times x plus k times y plus L times z. Okay. X, y and z are the coordinates of the atom within the unit cell. So, x, y, z are the coordinates of the atom okay. And this phase difference delta is with respect to atom at x equal to y equal to z equal to 0. So, this is phase difference with respect to the atom of the origin. So, clearly if I put x, y, z 0, okay, then the delta will be 0. So, this delta is with respect is the phase difference of an atom located at x, y, z with respect to the atom located at the origin. So, what is the role of this phase difference? So, obviously, this phase difference will lead to interference, okay, and this incidentally I should mention that this expression can be used for all unit cell shapes, okay, not just the orthogonal unit cell. So, valid for all cell shapes. Okay. It is most easily seen in the case of orthogonal cells, but this is in general valid for all cell shapes. Okay. So, now how does this affect the geometric structure factor? So, the geometric structure factor F for HKL, okay. So, the geometric structure factor for the scattering from the HKL plane, okay, is given by sum over all j equal to 1 to n. These are the atoms in the cell, unit cell, okay. F j. So, that is the atomic form factor times e to the I delta of the jth atom. So, delta is the phase difference of the jth atom. Okay. And this is the formula for the geometric structure factor, and let me also put this in a box, okay, because this formula is very crucial. Okay. And you can, and the relevance of this f is that the intensity is proportional to f HKL square. Okay. So, the intensity is proportional to square of this scattering factor. Okay. So, therefore, if the scattering factor is 0 for some value of HKL, then the intensity of that peak will be 0, okay, even though it satisfies the Bragg scattering condition. So, this is the structure factor. Remember, the geometric structure factor is an additional effect on the intensity of peaks that already satisfy the Bragg scattering criterion. Okay. So, now let us take the example of FCC. So, in FCC there are 4 atoms per unit cell. Okay. And these are there are 4 atoms per unit cell. Now, if you take the unique atoms means not those that are related through a lattice translation. So, if I draw my okay, and let me take my origin. Let me take my origin here. X, Y, Z. So, now I am going to take the four unique atoms. I am going to say are this one at this corner, okay, which due to lattice translation will be due to lattice translation, this same atom will appear at all the corners, all the 8 corners. So, I have the first atom at 0, 0, 0, which through lattice translations generates all the generates 8 other atoms. Okay. The next atom I will use a different color, okay, which I will take it as right at this phase center. Okay. And this through lattice translation will generate another atom here. And the coordinate of this atom is x, the x coordinate is fractional coordinate is half, y fractional coordinate is half, the z fractional coordinate is 0. Okay. And you can see what are the remaining 2 atoms that I need to consider. I will consider one in the yz plane, that is right here, okay, at the center of this phase, and that will be reproduced right in the center of this phase. Okay. And this atom has coordinates of the x coordinate is 0, y coordinate is half, z coordinate is half. Okay. And I need to consider one more atom, and that I will choose along the xz plane, and that will be right here, this atom in purple, which will be translated due to translations, it will also appear here, and the coordinate of this atom is half, y coordinate is 0, z coordinate is half. Okay. So, these are the 4 unique atoms, and we saw how with lattice translations they generate the entire FCC crystal. So, the 4 atoms per unit cell are these, and now let us calculate the geometric structure factor. So, now we can calculate f of HKL. Okay. This is given by, now there will be an atomic form factor. Now, if you assume that this is a monatomic FCC, okay, then all the atoms will have the same form factor. So, you will have f e to the I. Okay, now, what is delta for 0 0 0? Delta is 0, okay, plus f e to the I. Now, the phase difference for this is half h by 2 plus k by 2. Okay, and you can see you will have the phase difference for this is k by 2 plus L by 2 plus f e to the I h by 2 L by 2. Okay. Now e to the I times 0 is 1, and I have missed a factor of 2 pi. There should be a 2 pi in each of these. Okay. And now e to the I times 0 is 1, okay, and let me just take f as a common factor, and I have 1 plus. Now, this h by 2 plus k by 2 into 2 pi is same as e to the I pi into raised to h plus k, and then I have e to the I pi raised to k plus L plus e to the I pi raised to h plus L. I have deliberately written it this way, because I know that e to the I pi okay, this is cos pi plus I sin pi. Sin pi is 0, cos pi is minus 1. So, this is equal to minus 1. So, therefore, you have f of HKL is equal to f times 1 plus minus 1 raised to h plus k plus minus 1 raised to k plus L plus minus 1 raised to h plus L. Okay. So, you can see that if h, so if h plus k is odd, if h plus k is odd, okay, if h plus k is odd, then this term will be minus 1. Okay. If h plus k, okay, now if k plus L is odd, this term will be minus 1 and so on. If it is even, if h plus k is even, then this will be plus 1. Okay. So, now you can see that if h plus k, k plus L, h plus L are all even, okay, if these sums are all even, okay, then each of these will be 1, and you will have a structure factor that is 4. So, and in fact if h plus k plus L are all odd or all even, okay, if they are all odd or all even, then each of these sums h plus k, k plus L and h plus L will be even. Okay. Then you will have f of HKL equal to 4f. Okay, and this is the condition for observing the peaks. Okay. If H plus k, if H k are odd and L even, or vice versa, or you can have H k are even and L odd, okay, then you will see that H and k are odd. Okay, so H plus k will be even. So, its sum of two odd numbers is an even number. So, H plus k will be even. So, this will be 1, but since k is odd and L is even, k plus L will be odd. So, this will be minus 1, this will also be minus 1, H plus L will also be minus 1. So, in this case you will get f equal to 0. Okay. So, basically what you will find is that the condition for the peaks is that condition for observing the peaks is that H k L should be all odd or all even. Okay. This is the condition for observing the peak in the diffraction pattern. So, even though you may be satisfying Bragg's law, okay, the peak the values of H and k which are in which they are not all odd or all even, okay, will not contribute, will not show up in the X-ray diffraction pattern. Now, you can also do this for you can do this for different structures. Okay. In general, the condition for observing the peaks, condition on HKL for observing peaks. Okay. So, this is for a primitive structure, there is none. Okay. For a face centered, we already saw that HKL all odd or all even. Okay. For a body centered cubic, okay, the condition is that H plus k plus L should be even. For a C centered cubic, okay, you have H plus k should be even, and for a R centered, that is in the rhombohedral structures, you have L plus H minus k equal to 3 is a multiple of 3n, that is multiple of 3, or L minus H plus k equal to 3n. So, only peaks that are observed are those where L plus H minus k equal to 3n or L minus H plus k equal to 3n. So, I would expect you to know all these rules, okay, or because these are very quick. I mean, if you know these rules, you can quickly apply it to say whether the peaks are present or not, and so all other peaks are missing in non-primitive structures. So, all other HKL values do not show peaks in diffraction pattern. Now, before I conclude this lecture, I will just say that you can do this, you can also do this for multi-element solids. Okay. So, let us take the example of NaCl. So, in NaCl, you have an atomic form factor of Na and an atomic form factor of Cl. Okay. And now, if you write the structure factor, let me draw the structure of NaCl. So, I will draw Na in blue, Na atoms in blue. So, sodium atoms will form a face centered lattice, and let me put the chloride ions. The sodium ions will be in this face centered lattice arrangement. The chloride ions will be at the edge centers and the body center, okay, and also located at the body center. Okay. The body center will be located will be located at some height off the screen. Okay. So, the sodium atoms, and these are the chloride ions and sodium ions, and now we can write the structure factor. Okay. I won't discuss this in detail, but you can see that you have F Na, okay, and now you have 8 atoms per unit cell. Okay. F Na into 1 plus, again it will be just like what you had in the FCC, H plus K pi, or let me write it since we know this answer, minus 1 raised to pi plus minus 1 raised to H plus K plus minus 1 raised to K plus L plus minus 1 raised to H plus L, plus you will get the terms due to the chloride ions, and here the chloride ions. Okay. So, the location of the chloride ions, okay, is basically at you need to consider 4 of these chloride ions. Okay. One will be at the center of the cube, at the body center, okay, and the remaining 3 will be this, okay, and there will be one perpendicular to the screen, okay, that will come directly above this point, okay, at the center of the face, that is at z equal to half, and there will be above this at z equal to half. Okay. So, you can write the coordinates. Now, the first chloride atom is at will be at x equal to half, y equal to 0. So, this is half 0 0, and this is 0 half 0. The third one will be 0 0 half, and the fourth one will be at half half half. Okay. So, it will look like e to the I pi. Okay, I have taken the factor of 2, and I will have h plus e to the I pi k plus e to the I pi l plus e to the I pi h plus k plus l. Okay. And this whole thing is multiplied by the form factor of chlorine. Okay. And you can analyze this for different values of h and k, h, k, l and l, okay, and you can find out what the peak will be. So, for example, if h, k, l is all odd, or all if h, k, l are all even, okay, then each of these terms will be 1. Okay. So, then the structure factor will be F Na. So, 4 F Na plus F Cl, okay, and that will be the maximum of the intensity. Now, if H, K, L are all odd, okay, then the structure factor will be 4 F Na Okay. So, plus now in this case minus 4 f Cl. Okay. So, because each of these e to the I pi h will be minus 1, e to the I pi k will be minus 1, e to the I pi l will be minus 1, e to the I pi h plus k plus l will also be odd. So, that will also be minus 1. Okay. So, you can do the structure factor for multi element solids in this way, and you can generalize it to all kinds of solids. So, with this I will conclude the second lecture of week 9. Okay, and here we have seen how to calculate the geometric factor in detail. Okay. Thank you.